Hello everyone. Is this working? Yes, I can hear it now. So, imagine you have a lot of devices on the field, many devices, and at some point, some devices are starting to fail. What happens? Your customer are starting to tell you, please fix this as fast as possible. Your boss is pushing you to find a solution, to understand what happens, and then you have your device and you need to investigate. Besides, I guess you know that recently we had some kind of security rules that are coming, the RED, the CRA, Resilience Act, that are pushing people to add security in their devices, to provide a secure boot, a secure firmware update to be able to perform for, OTA or local updates and to close their device. So on one hand, you have to understand what your device, why your device is not working. On the other hand, the device is closed, it has a secure boot. So what do? You have your device that is kind of a black box. So here is the purpose of this talk, is to explain you one solution that ST is providing on their new devices to address this kind of issues. So, you have your device on the field, the firmware is protected, you have this secure boot that requires your device to be closed because or not of the CRA. It could be for other reason that you need a secure boot. So you then have a device that is failing. You don't know what the reason could be. A failure in OTA, could be a hardware issue, unexpected outputs like here. You don't understand what happens. So you get back your device. Usually with the STM32, it's smaller than that. But the impact of this failure could be critical, especially for the trust of your company in front of your customers. It could be also a problem, impact your business if you don't manage to solve rapidly enough the issues that you have. It could become known, and so you will have business impact, and also bringing back the devices will cost a lot. And you have also the complexity of analysis, because today software are getting bigger and bigger. You don't control all pieces of your firmware. And also the issue could be difficult to reproduce. So the time to understand this is the issue. One solution that we propose is the capability to reopen the device securely. So you have a closed device that is secure. We propose a solution to reopen it for debug, to be able to attach a debug probe, but in a secure way. And I will explain how it works. So the solution, we call it debug authentication. So we authenticate, we have a way to authenticate who wants to debug the device. So the main features are secure reopening of the device, also the capability to regress the device. So regression is the capability to erase everything without knowing the content of the flash. It's what we call a regression. And also possibility to reopen it partially, and I will explain you why it is interesting. This solution is based on the ARM ADAC protocol, which is a standard protocol, and moreover, it is certified. So this certification means that you cannot use this mechanism and with a kind of local attack using glitches on the board to be able to reopen it if you don't have the credential to reopen it. So it's an insurance that this mechanism is robust to hackers. So just to give you a way to see how things have evolved at ST, because we try to give the best experience to our customers. So we started with this protection of the device that was called RDP, that is still called RDP1, that allows you to do a regression. So when you receive the device from the field, you can regress the device, put another software, firmware, and investigate, but you have only hardware investigation in that case. Then we had this RDP level 2, where device is closed. In that case, the level of security is much higher, but the repair capability is lower. You have only a black box to understand what happens. Then we introduced a regression, a keyed RDP, meaning that you have the possibility on, for example, STM32U5 to add a secret key at production time and to reuse this key to reopen the device when it comes back for repair. And in that case, you are able to do a regression like in RDP level 1. And the last step is this debug authentication, where you have at the same time a very high level of security and a very good repair capability, even higher than what we had before. So I will explain you now the principle of debug authentication. Just, it's like a door lock. When you have a door lock, the door lock is public. Anyone can access to a door lock, and it's like your device, it's public. And you have the key to open your door. And the key, this is what allows you to open the door. This is the private key. This is what we have. So we use the same basic mechanism. If you have the private key, you can open the device. If you don't have the private key, you cannot open the device. But it's a bit more complex than that, but that's the main principle. So the door lock is public, the key to open. So with debug authentication, we have a public key that is inside the device. So the public key is what is public, what you can access to. The private key is in your safe at your premises, is what will help you to reopen the device later. And only you can open the device. So where are the keys? You need to generate a key pair, basically, and put the private key, so what we call a root private key, inside a safe. It should never be exposed like the keys you use for your secure boot, for example, to sign your secure boot. It should be in a safe, and most probably in a HSM to make it really robust. And you have the root public key. And what we are doing is, at production time, we provision the root public key inside the device. So this is the only thing you have to do, and it's like with the U5 when you had a secret that you need to provision during production. You have this to do it for debug authentication also. So this is the only thing you need to do. There is a second thing to do, but that is the debug authentication maximum capabilities, but I will not go into too much detail here. So here I will show you, it represents the content of a firmware of the STM32 microcontroller, a typical secure application. So you have a secure boot with the keys for the secure boot, the data. So you boot on your secure boot. Then we have a mechanism that is called HDP that isolates the secure boot from the next stage. So when the secure boot has authenticated the next stage, the secure firmware, for instance, it jumps to the secure firmware, and the secure boot is not available anymore. And there is a second level of isolation that is trust zone. So on the new Cortex M33, for instance, you have this trust zone mechanism. So on one side, you have the secure firmware, and on the other side, you have the functional firmware with its data. And usually, all the firmware is here, and when you need to use cryptography to sign a message, for example, you need to call here a service inside the secure firmware, and this is restricted to a specific gate. So this is kind of typical application you have: secure boot, secure firmware, and functional firmware. So now, this is on the field, and you take it back from the field. It is closed, so you cannot access anything. And then you can reopen only this part. If you know that there is an issue in the functional firmware, you can debug what is in this functional firmware without touching anything and having access to any part inside the secure application, and neither in the secure boot. And you can also, if it's required, reopen this or reopen everything. So this is an example of what can be done with debug authentication. You have the ability to selectively reopen what is needed. Now, to be able to reopen this, we use a mechanism of a certificate. So the certificate will contain information that will give you this control. So a certificate is basically a public key, always. You have this information in the certificate, which is the ability, so debug authentication ability, meaning that with this certificate, you will only be able to reopen the top part, or the two, or everything. Or it's up to you. You have also one very important point is that you can put the device identifier of the device you want to reopen. And you will see just after how powerful it is. And then you have a signature. So the certificate is signed. And this is a standard way of managing cryptography. So we manage certificate chain. So you remember we had this root key, so the root private key, root public key. And from this root public key, we generate a root certificate with the maximum debug authentication capability we want. And we sign it with the root key, so it's an auto-signed certificate. Then we have to create an intermediate certificate that is also signed by the root key of the root private key that we have. And then we have what is important, the leaf certificate. So this leaf certificate is the certificate we will need to generate when we want to reopen the device. So this certificate will be created when the device is back from the field. And so we have the device, and we are able to read the device identifier from this specific device. So we read the ID, device ID, and we put it in the certificate, and then we sign the certificate with the intermediate private key. And this certificate is, together with the private key that you have created, is the key to enter inside your device. So you can see that with this certificate, we know that we can open a certain device with certain debug authentication capabilities. So the first step is to get the certificate. So now you got the device back to your premises. You read the unique ID of the certificate. You generate a key pair. And then you send this data to the certificate authority. So this should be in your company the guy who is responsible for the security, who has access to the root private key or the intermediate private key, and is able to give you this permission. So it can talk to your manager to understand what level of reopening you have access. So you select the reopening level, and then you create the certificate. You create a certificate chain containing the root, the intermediate, and the leaf certificate. And this certificate is associated to the device. So the second step, you have the certificate, you have your private key, the device, and you use a PC to communicate, and then you send the certificate chain. The device contains the public key, the root public key. So with the root public key, it can check the signature of the root certificate. It can check the signature of the intermediate certificate. Then we have authentified the public key of the intermediate, and then we can check the signature of the leaf certificate. So we are sure we can trust now the public key of the leaf certificate and also the content, the device ID and the debug authentication. So we can already check that the device is the same. We can read the device ID here. So the second step is to generate a random that will be signed using the private key. So the leaf private key will be used to sign this private key. And if the signature check is OK, then you request to reopen the device at the level you want. So this is how things work. So it's very, very flexible in the way you manage it. You can see that you give the ability to someone to reopen only one device, so it can investigate in one device at a certain level. So this is what you get. For example, the certificate allows you to investigate at this stage, or at any stage you are authorized to do, depending on your issue, what you want to investigate. So this is the debug authentication is the solution that we provide to address this kind of issue. So this is secure. So it's you can see that we use really the security, the private key, public key mechanism to be able to reopen it. It is flexible because we can reopen at different level of the software, and it is certified. And today it is available on STM32H5, on the H7RS, and on STM32N6. And if you want to discuss more in detail, I'm available on the booth to answer to your question. You can ask now a question if you want about this mechanism. Who will be the first? Anyone? It was very clear? Thank you.
So in the secure mode that the MCU is in the field, what's your communication link then to ask it for the ID and to communicate the certificate?
That's a good question. I didn't address that. The communication link is the JTAG. So we have, with this device, 2 JTAG access points. So it's JTAG or SWD. It's working with both. So we have an access point for debugging that is dedicated to debug, and a second access point that is dedicated to communicating only with the debug authentication firmware that is inside, and that is implementing all these mechanisms to check the signature and to reopen the device. So this is important. You need to leave access to the JTAG to your device to be able to do that. Is it answering your question? Yes? Okay, thank you. Don't hesitate, no problem. I'm here to answer. Okay. So thank you for your attention. I hope it gave you a good view of this mechanism. Thank you.